Okay. Okay, so we are starting a new section. We are starting our section on torsion. And on Friday, we developed a new equation that shear stress because of torsion is T rho over J. And we also have that the maximum shear stress is TC over J. So as I look at my cross section and I'm twisting about that centroid with an applied torque or an internal torque, resisting torque that's acting on that cross section, okay, I have T. And when I look at C over J and rho over J, these are like the stress equals P over A. It's the geometry of my cross section. So C equals my radius. C is max. It is the point out here on the edge. Rho is some distance along that radius. Okay, it's my radial length. When rho gets to the outside edge, rho equals C, and that's where we have our maximum occurring. But we could also find the shear stress at halfway out. Okay, so we've had P over A, that's where we have longitudinal, and we're pulling straight through the axis, and we can look at a cross section, and it is the internal resisting force P divided by the area gives us our stress. Now we are looking at the same system, but we're going to be twisting it. Okay, we're now twisting it out like a wash rag. Twist, twist, twist. And it develops shear stress. Okay, shear stress. So, with shear stress, we have to recognize, okay, what is shear stress? It's parallel to that cross-sectional area, and it's going to cause a distortion where we have shear strain. So when we're looking at shear stress, then we need to be looking at, it's like our stress equals E times strain, except now we're looking at the shear version. So we have shear stress, we have that deformation that occurs, and that deformation is a function of our material property. This is the shear modulus of rigidity, or the shear modulus. Okay, so it looks like this, except this we developed in tension. This we're developing by skewing it. Okay, so it's like when you apply the brakes on your bike and that rubber pad squeezes in, but you can also see it's going to be till we stop it and comes back. So we have that shear strain. So if we have shear strain and we have this shear modulus of rigidity and we have shear stress, our stress again is just a function of resisting force and cross-sectional properties. The amount that we're going to skew over, the amount of that shear strain, is a function of the material properties, just like we did with E. Okay, so we haven't covered this yet, but on Monday we will be developing a new equation, TL over JG. This has to do with that rotation. It has to do with how much am I skewing over, and it looks a lot like delta equals PL over AE. How much am I stretching? How much am I rotating? Okay, we can see they both are internal forces, so this comes back from statics. If I were to figure out internal forces, and we don't really look at torque in statics, but we could look at torque. We have an internal normal, torque, moment, and shear. So we're dealing with this internal resisting torque. Length, just like what we had with delta. G is the equivalent for shear as E is for normal. Cross-sectional property, so geometry, J, polar moment of inertia. It is also cross-sectional property. Remember, C is radius. So the equations are set up very much the same. So we have a solid circular steel shaft having an outside diameter, pure torque. So torque tells me I'm going to be dealing with shear stress. That's for my maximum. And I'm going to have a twist. Okay. So I have an outside diameter of 35 millimeters. So I'm going to draw this. That's my diameter. But I have to recognize that my equations actually deal with the radius. So I'm going to rewrite it that my radius is d over 2 is 35 millimeters over 2. And I get 35 in there, 2 divided by, I get 17.5 millimeters. Okay? I also need to recognize that in SI, we deal with newtons and meters. So I'm going to go ahead and rewrite my radius as 0.0175 meters. So I've got the radius figured out. It's a pure torque. Our torque is 640 Newton meters. Okay? It is in correct units. So that would be like if I had, a system of pulleys and gears, and I said, well, for this segment right here, what's going on? So I could cut it, I could find my internal, and that would be my torque for that section. So we're just telling you, instead of making you go through all of this work, we're just telling you the torque is 640 Newton meters. Okay? And I have a shear modulus of 80 gigapascals. And again, I don't like to have anything but Newton meters, and I don't want to have to think. So it's 80 times 10 to the 9 Pascal, which a Pascal is a Newton per meter squared. So I can do a unit check really quick, and my units are all good to go. So the first thing I want to do is I want to find that maximum shear stress. And I know that occurs at C, which is my radius. And I've been given torque of 640 Newton meters. My C value is my radius, so 0.0175 meters. J is for a solid pi over 2, C to the 4th, 0.0175 meters to the 4th. So everything I've put in here, we check meters, check Newton meters, check meters. So now I just need to set up my problem. So I have 640, 0.0175 times, whoops, and then I have pi as a number, 2 divided by 0.0175 to the 4th times divided by. So you can see I get this gigantic number. I don't want to write all that down. So this is in Newton per meter squared. Okay, that's a Pascal. So now I can go 1, 2, 3. I can move it over 3, so now we're at a kilopascal. 1, 2, 3 megapascal. So my shear stress equals 7602316.5 pascals, which is a Newton per meter squared. Okay, so 1, 2, 3, 4, 5, 6. So my shear stress is 76 megapascals. Okay, so how does that affect my system? What kind of rotation do we get? Rotation equals TL over JG. Okay, well, my torque was given at 640 Newton meters. It gave me a length of 1.5 meters. My J is still pi over 2, 0.0175 to the 4th. And my G is 80 times 10 to the 9th. Newton per meter squared. So if I look, I have Newton meter, Newton per meter squared. So my units are working out correctly. And so now it's just a matter of multiplying. So I have 640 times 1.5 divided by pi as a number, 2 divided by 0.0175 to the 4th, 80, 10 to the 9th, times divided by. And I get this very tiny number, as I should. It's in radians. Remember when we look at shear strain, we're looking at that strain, that gamma, it's in radians. So this is in radians. So I get 8.145 times 10 to the negative 2 radians. Okay, and I could rewrite that as 0.08145 radians. Okay, so now I should ask myself, is this a realistic number? Does this kind of a twist make sense if I'm looking at small deformations? Well, how do I go from radians to degrees? I just remember that if I go around a whole circle, I've gone 360 degrees. If I go around a whole circle, that's also 2 pi. Or if I go around half a circle, it's 180 degrees. Half a circle is also pi. So it's easy to keep this relationship. If I have radians on the top and I want degrees, then I need to set my ratio up like this. So I could say, well, let's just check to make sure what kind of number is that, 180 times, and then divide by pi, and I get 4.67 degrees. Okay, so for me, it's visually it's easier for me to understand this than to say, well, what does a radian mean? Okay, if I had, like, you know, I'm twisting 90 degrees, I might want to go back and reconsider maybe some of my numbers. The other thing I should always do, which I didn't do here, is if I got that my shear stress is 76 megapascals, I should make sure that is less than the yield. Okay, because this equation again is only valid in the elastic region, just like what we did with normal stress. So I should go back and say, okay, if it's a circular steel shaft, what is the yield stress of steel, and am I underneath it? And I should find that I am, so check, check. That means this phi is a valid solution.